In this video, we'll discuss the operations on a B tree. The first operation is creating a B tree, that is just the constructor, and we discussed in the previous video that we have different members in the node of a B tree, and among those members are some arrays. So we would just initialize those data members in this first operation. This We'll discuss in some coming slides the search operation, and then we'll discuss the insert operation in this video. In the next video, we'll discuss the delete operation. So let's start with the search operation. So searching in a B tree is very simple. It's very similar to a binary search tree. So what we do is that in the BST we would actually perform a two-way search. On every node we would compare the value of that node with the value to search, and if the value is available in this node we just return the index. Otherwise, if the value is smaller, then we move on the left branch, and if the value is bigger, then we move on the right branch. So it was a two-way decision for a binary search tree. Okay, whereas in this m-way search tree we just extend this operation to be the m-way operation. Okay, so for example, if in this given tree we want to search 40, what we would do is that we would start the search from the root node. So this is the first disk access that we might have. Okay, so this is the access. Now we have an array of values in the root node. And the array is sorted. So we just search this 40 in the sorted array. We found that the value 40 is bigger than 13. So we should go on to this child, the second pointer of the root node. So we make another disk access and read this node in the RAM. Then we search the 40 value in the keys of this node. The array is sorted, so we can perform a binary search here. Okay, so binary search is only log base of n. So the worst case is log base, because we can have m minus 1 key log base m minus 1 operation. So that's a very small operation. The value of m is closer to 100, or maybe a little bigger than 100 usually. So this would not take more than 5 to 10 operations. So performing a binary search, we see that 40 is bigger than 31 and smaller than 43. So we move on to this pointer and we perform another disk access. We reach to this node, and upon searching in this node, we find that the value is smaller than 41 and bigger than 37. We move on to this pointer, which is a null pointer, which contains the null address. It means that the value is not available in the B tree, and we had only 3 disk accesses. Okay, so this is the search operation, and if we find the value somewhere between on this branch, we just terminate the operation and return the value, or just return the status that we have found the value. Okay, so this is the path that the operation took. Okay, so this search operation, if we just look it a little more critically, in the databases, as I just discussed, that a B tree is actually the indexing mechanism in a database. So this blue writing here is an SQL, structured query language, that is used to give commands to a database management system. So in this SQL, what we are doing here is that we want to read static, means all the values. We want to select all the values from the database. Maybe this is a table actually. So we want to read all the values from this database where the values are greater than 10 and less than equal to 25. So this gives us a range between 10, all the values between 10 and 25. So you see, uh, if we want to find a range, B tree is very suitable for this operation, because what it would do is that it would actually pick a pie shaped portion of the B tree, which says that all these values are bigger than 10 and bigger than equal greater than equal to 10 and less than 25. It's the entire, all the nodes in between these two endpoints. So it would actually pick a slice from the B tree and return it to us. Okay, so BT is very efficient in performing these type of operations, whereas for the other trees, we would actually need a very inefficient operation. A BT is very efficient in doing such type of operation. So search, a related discussion on the search in the BT is the query of, in fact, we say these queries as range queries. So we actually we can perform range queries efficiently using a B tree. Okay, so that's the search operation in the B tree. Let's move on to the insert operation in a B tree. This insert operation is actually a little complex, so we'll discuss this in different components. We would divide it into different components, and then we'll discuss those one by one. So the insert operation, for an insert operation, what we need to do is we actually follow the same idea of a binary search tree, that we would actually find the appropriate position or appropriate leaf node where we need to insert this new value. So all the new values go into a leaf node definitely, but similarly in the search tree fashion. So it goes into a leaf node, and then um, when we insert the value in the leaf node, there can be a case we need to check if the node is already full or not. If the node is not full, we just insert the value and do nothing. Otherwise, if the node is full, then we cannot insert the value, just insert the value in that node. We insert the value and we split that node to make two nodes out of one and divide values appropriately or accordingly. So look at this scenario. In this specific scenario, um, this is a five-way tree. Okay, so five-way tree, it can have actually for every non-root node we can have 5 by 2 5 by 2 children, that is 3 children, and 2 keys. So this node has 2 keys, so this is a valid B tree. Now if we want to insert into this node, insert 10 into this node, into this tree, what we do is that we just perform this search to reach the value where we reach the node where we need to insert 10. So 10 is bigger than smaller than 12, so we need to move on to the left branch, and this is a leaf node here, and it has this one space left empty here. So we would just copy this 10 here, and no further operation is required because this there was space for accommodating 10 in this node. Okay, so no other operation is required. So this was the first scenario when there was enough space in the leaf node to adjust a new value. Okay, now let's move on to the next scenario where the leaf is full. So if the leaf is full, we call this node, for example, y. So it has, if by full it means it has m minus 1 key. That is the maximum number of keys that a node can have. So what we would do is that we would actually split that node. If it has m minus 1 keys, what we would do is that we would split it from the center and make two nodes out of this one node. And if we divide the values equally, it would have m by 2 minus 1 keys here, m by 2 minus 1 keys on the right side, and 1 key would be the central key. Okay, so let's see how it is done. So this central value, it goes into the parent. So as this value would go into the parent node, it would go upward. Okay, so B tree is a tree that grows in the upward direction. That's very unlikely here in the data structure schools, because all the trees that we had, they were actually upside down. The root was on the top, and then it would grow downwards. Remember? But in a B tree, it actually grows upward, and this is something very uncommon in data structures course here. So the value goes upward and it would go into the parent, and if it goes into the parent can also be a full node. It needs to be split again. Okay, so this process can move up the way, up to the root, all the way up to the root, and what it can do is that it can actually split the root as well, resulting into the addition of a new level. Okay, so when we split the root node, we actually move one node above and make it the parent, and that parent would be the new root node, and the previous node root node would divide or split into two children of the new root node. So that's how a B tree increases in levels. Okay, so if y has no parent, then the tree grows in the height by one. That is the scenario that I just discussed. So let's see the example that in the same tree we insert 11. So it's the smaller than 11 value, so it goes into this node, but this node is already full. So we place this 11 in the sequence of these values, and then pick the median value. There are 5 values, so the median value is the third value. So this 8 is the value on which we split this node. So when we split this node, we would have 2 and 3 in the left split and 10 and 11 in the right split. And this 8 would go in the parent. So if it goes into the parent, what it would do is that it would just move this 12 towards the next index, and this root node would be like this one. It would have 8 on the first index and then 12 on the second index. Okay, and these two splitted nodes, these two nodes, they would actually the left and the right child of the value 8, because these 10 and 11 were bigger than 8. So these become the right, this node becomes the right child of 8, left child of 12, and the right subtree remains the same. Okay, in this specific scenario, this root node actually accommodated the new value. Okay, had this root node been full, then we would have split this node as well and moved another key on the upper level and increased the tree by one in level. Okay, so that's the scenario. So um, in this is the final shape of the tree. So that I just discussed in the previous slide, that 8 moves up in the root node, and the left child of 8 is 2 and 3, contains the value 2 and 3, and the right child contains the value 10 and 11. So we have more children of the root node. So this is how this B tree accommodates values in the last level. And you can clearly see that we cannot ever have a leaf node on the upper levels, because these leaf nodes, this new node is actually a leaf node here, because the increase was, the key was the difference that it made, this operation made, was that it moved one key upward. So leaf node can never be created in the levels up in the tree. Okay, so let's see and let's discuss another scenario. As we see that if we when we split the node, we move one key upward, and if the parent is full, we split that parent too. uh, and this process can go out all the way up to the root node. So it means that when we search the key, we moved down and performed this downward pass in the B tree. And when we inserted the value in the last node, in the leaf node, we split this node, and then we need to perform this split all the way up to the root, which means that we now have two passes in the B tree. And remember, every um, every node access, we count it as a hard disk access, IO access, input output access. So if we need to perform 3 hard disk accesses on the way down to the leaf, then we need to perform the same number of disk accesses all the way up to the root again. So it would double the number of hard disk accesses. So we do not want to do that. What we would do is that actually uh, we would just try to avoid this second pass. So in order to avoid the second pass, what we do is that when we actually descend down the tree, we simply split all the full nodes that we see on the way downwards. So if the root is full, we just split that root node, and then we go to the respective branch of the tree. And then similarly, if we find another full node, we just split that node and then go downwards. This way we can avoid the second pass. Of course, there is a problem, and the problem is very simple, that it may result in unnecessary split operations, of course. But does these split operations decrease the performance of the B tree? No, because it actually avoids the second pass in the B tree. Okay, so this is actually very this operations is what uh, uh, we can actually have here. Okay, so since the split operation is in the linear time, we just find the median value in the maybe binary search. So we find the median value just by dividing the n by 2 and find the n index, and then we just create another array, copy the values there, so it's a linear operation. Okay, so the running time of the B tree is not affected much. Running time the B tree insert operation is not affected much. So we actually allow these unnecessary split operations before going before finding the node. Okay, so this is one efficiency that we would actually like to add into this simple operation. Okay, so now we'll run one example, and we'll see that how we can create a B tree from scratch. So given these values C and GA, these are the keys that we want to insert into the B tree. So, and the tree is of order 5. Okay, so this is the information that we have. So let's draw this tree one by one. So for example, if we have if we want to insert C in in an empty B tree, what we simply do is that we would actually create a root node and insert the first value C in this root node. So root node is the only node, it is the leaf node as well, so it has the value C. Okay. Okay, now we want to insert n in this node. So what we do is that we come to this node, and this node has space. So we just insert this value C, this n, into the ascending order. So n is bigger than C. So what we would have is that we would have n here and another pointer here. Okay, so this is how we insert n now. Okay, then we need to insert G. So this root node has space to accommodate G, because for the order 5, we can have 5 minus 1, 4 keys in the root node. So inserting G is bigger than C but smaller than N, so we need to perform a sorted insert. So G would come between C and N. So this is C, G, N. We still have one, we can still add one value in the root node. So for A, we would add A as the first key in the root node. So this is the full root node. Any new insert, for example, when we insert H, we would need to split this root node. So now we would need to perform a split operation to insert H. So in the ascending order, A, C, G, and then we would have H and N. So we would put all these keys in the ascending order and find the median key, that is G. That's the third key here. So what we would do is that we would split the root node. We would put A and C in the left split, and H and in the right split, and G would move up. And since there is no parent, so G would become the root node. AC would be the left child and HN would be the right child. So this is how we perform the split operation on the root node, and the tree grew in the levels. So now we have actually two levels. This is the level 0, this is level 1. And remember, we first filled the root node, and then we actually increased in the level. So that's the essence of a B tree. So we actually have the entire simulation here. So after inserting H, we would have the split operation, and the node G would become the new node. Then we have this value E. If we want to insert this value E is smaller than G. Now we would not insert the values in this root node, because the value, it actually performs the search operation and finds the leaf node where it needs to be inserted. So E is smaller than G, it goes into this branch, and it would insert after C. Okay, so this is the way we would insert the value E, K, and Q. All these values need no split operation. So E is adjusted here, K is here, and Q is here. So one value went into the left child, and the two values went into the right child. So after Q, we have this value M. M is bigger than G, it should go into this node, but of course, this node is the full node because we can have, for order M, we can have maximum 4 number of keys. So for M is actually the value that should be after K and before N in this node. So when we insert M in this node, uh, actually M is the central value, the median value as well. So we would split the node, move M upward, and H and K would be the first split, N and Q would make the second split. And M would go into the root node, and HK would be on this pointer, and the new pointer would point to the right split, that is N and Q. Okay, so that would be the tree after inserting M. I hope this makes sense. So after inserting M, we would split the node and move M upward because it was the central value, and HK was the left, it becomes the left split, and NQ becomes the right split. Okay, so that's the split operation. Then after inserting M, we have this value F. F simply goes in this node, then W simply goes in the last node. L is the value that goes into the second node, and similarly T is goes into the into the last node. So F, W, L, and T, they are simply F, W, L, and T are simply adjusted into the already available nodes. Now after T, we need Z, and Z should go into this node, which is a full node. So it would split. Z is the biggest value, so it would split on the value T. In order to insert Z in the tree, we need to split this rightmost node on the value T. T would go into the root node. This left split is already pointed to by this pointer, and the new pointer would point to the right split, that is W and Z. Okay, so upon insertion of Z, the tree takes this shape. T goes in the root, and NQ is the left split, WZ is the right split. Okay, then after Z, we have P, which would go into this node. Then we have R, that again goes into this node at the last spot. So after inserting uh, P, R, X, and Y, X and Y is of course X and Y would go into this node. Okay, so all these four values would be inserted without any split operation. So after those inserts, if we want to insert D, would it have? This node is full, this node is also full now because two values went into this node and two values went into this node. So these two nodes are full. Now we want to insert D. D goes into the left left child of G. So D goes here. Okay, so we need to split this node, and the median value is again D. It would go into the root node. So, and in the root node is the smallest value, so D goes here, and the left split is pointed to by this pointer, and the right split is pointed to with by this pointer. This is the right split is E and F. Okay, so after the insert of D, we split this node, and we made two nodes and moved D upward in the root node. Now root node is full. See, so and we are left with one value, that is S, and it should go into this node which is already full. So you see, now we have come to the point when we need to split this node and then move one value upward into the root node, which again is full, and we would need to split this node as well. So if we just perform this insert operation into the value into this node, P, Q, R, and S. S is the biggest value in this node. So we would need to move this Q upward. Okay, so we would split this leaf node. Left split would be N and P. Right split would be R and S. Okay, this q would go upward. So q is actually the biggest value in the root node, so we would need to split this root node on the value m, so m would go upward. So this would become the left split and t and q would become the right split, so and m would be the root node. So the final tree would be something like this: m is the new root node, d and g are the left split, t and q are the right split. Okay, now, one more thing here that you need to ensure here is that when we split this root node, it has a few children as well. So we need to adjust those children accordingly. So when m goes upward, this child, this n and p child, this would actually become the left child of t. Okay, then these r and s, they would become the center child of this node, and x w x y z would be the third child of after the q. Okay, and all these three children, these three children, they would actually be would remain the same, that this h, k and l will become the right child of g. Okay, so that's the final scenario. After inserting s, we have these three children in the left subtree and these three children in the right subtree. So we actually split the children as accordingly as well. Okay, and we have increased the tree in height by 1. Okay, so that's how we perform the insert operation in a B tree. Um, and in the next video, we'll discuss the delete operation in the B tree.